So this one is Pop Quiz 90, which is related to organic chemistry. The first one discussion is about alkenes. Alkenes contain a carbon to carbon double bond that consists of a sigma bond and a pi bond. So when there's a double bond, one of the bond is a sigma and the other bond is a pi bond. Complete a diagram to show the areas of electron density for each bond and label that as a sigma bond or a pi bond. So we have to show the electron density, like the region of finding electron is maximum, that we have to show that region. So sigma bond is formed by a complete overlapping. So the complete overlapping will result in a formation of a sigma. So this region will have a sigma bond. So we'll label that as a sigma. And a pi bond, how a pi bond is formed when the orbitals are parallel, their axes are parallel, but there's no overlapping. So this will be a pi bond. Like this is one pi bond, not two pi bonds, because attraction is there from the top and the bottom. As a result, it will form a pi bond. So you have to show the electron density map. There's also another way of representing this. Like this is one way of representing. Then the other way, what you can do, you can represent the sigma and the pi bonds in this manner. Say you're representing this region as a sigma bond and the pi bond. This is collectively as one pi bond. Like don't consider there's two pi bonds. Like this is collectively a one pi bond and this one is a sigma bond. So you can also represent in this manner as well. Both are acceptable. Moving on to the next question. Propene is there, which is C3 and H6 is an alkene reagent needed for three reactions of propene are shown. One is steam and acid as a catalyst. Another one is acidified potassium manganate, and the other one is bromine. So steam and acid as a catalyst, what it will result? It will result in a formation of alcohol. Like the alkene will turn into alcohol. And if you use acidified potassium manganate, then it will produce diol. And if it is reacting with bromine, so there will be an electrophilic addition reaction. So we have to first complete like breaking the double bond here. So we can draw in the same manner as it is given. So we can show like here we have CH3, C. The double bond will break. The hydrogen, like one side H will be added and one side OH will be added. So how you'll know which side likely H will add? So according to Markovnich's rule, that hydrogen is added towards the carbon which is already having more hydrogens. So if you see, like when the double bond will break, we have on the right hand side a carbon with two hydrogens, and on the left hand side the carbon with one hydrogen. So where, because it is reacting with steam, steam means H2O or HNOH. So where the H will be added, H will be added to a carbon which is already having more carbon, more hydrogen. So hydrogen is added to a carbon which is already having more hydrogen. So this will be the product. Like the major product will be this one. That is a Markovnich's rule as well, or it's also related to the idea that when carbon cation is surrounded by more alkyl groups, it is more stable. Then the second one is acidified potassium manganate, seventh. It will change from purple to colorless, and as a result, it will produce diol. Means the double bond will break and the two carbon atoms will have OH group attached. And reacting with bromine, so same way, we break the bond. If they ask for the displayed formula, then we should represent all the bonds and all the atoms. Structural, so minimum detail we can show. Skeletal also you can draw in each. Draw the structure. So they did not specify. So you can draw any of the structure here. The next one, propene also react with hydrogen bromide. Give the mechanism of this reaction to form a major product, including a curly arrows and a relevant lone pair and the dipoles. So electrophilic addition, as I mentioned, reaction mechanism is important. You have to learn this electrophilic addition and the free radical substitution in alkanes. So we have CH3, CH, double bond, CH2. Now, when HBr is there, so H and Br, hydrogen will be partial positive and bromine will be partial negative. So bromine will take both of these shared pair, and a hydrogen is attracted towards the electron rich side. So we call this as a electrophile. So drawing arrow is important from double bond towards the positive center and from the bonded, like the shared pair between hydrogen and bromine towards the bromine. Now, second stage, what will happen? The bond will break, the double bond will break and a hydrogen will be added. Which one will have a hydrogen? The one which is having more, like if we break the double bond. So which one will have a hydrogen? Even you apply a Markovnich's rule that the hydrogen added towards side where hydrogen are more. So here we have two hydrogen, here one, so hydrogen will be added to this one, the major product. So this will be a carbon cation, and this carbon cation will be more stable. Why this carbon cation is more stable? Because it is surrounded by two alkyl groups. So this will be the carbon cation. Then the bromide ion now, which is having an extra electron, is attracted towards the carbon. As a result, it will form two bromo propane. So we'll have CH3, we'll have CH, Br is there, and then CH2, Br is there. So this is how, not Br, but actually H will be there because it is H reacting with HBr. So all have the same mechanisms, but the only difference is the starting reagents are different. Sometimes they ask with hydrogen chloride, sometimes hydrogen bromide, sometimes bromine. In part C, alpha occumen contain 3 carbon to carbon double bond. It is found in plants and has a sweet smell. The skeletal formula is shown. Give a molecular formula. So to give a molecular formula, because hydrogens are not given here, so means like 1, 2, 3, 4, 5, 6, 7. Because 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, and 8. And the double bond is here. Then this is down. And there's a double bond with this one. Then just put the hydrogen. You don't have to draw the structure just to make it simple. This will have 2 hydrogens. This will have 1 hydrogen. This will have 3 hydrogen. This will not have hydrogen because all 4 bonds are occupied. 2 hydrogen, 2 hydrogen. This will have 3 hydrogen and this will have 2 hydrogen. So you have to count the number of the carbon, the total number of a carbon and the total number of hydrogen, and that will be the molecular formula. When we count, like we will have 10 carbon and hydrogen are 6, then 10, and then makes it 16. So it will become C10 and H16. On the skeletal formula, draw a circle around a part of a molecule that give rise to a geometrical isomer. Look, to be a geometrical isomer, what should happen? It should have different groups attached to it, like carbon-carbon double bond. If different groups are attached to a carbon-carbon double bond, we call that as a geometrical isomer. So we have to check three regions are there. This is one region, this is a second region, and there's a third region of carbon-carbon double bond. We have to check these regions only. So if I consider this region, so this will be C and this is also C. Two bonds are there, so it will have hydrogen, hydrogen, and this will have hydrogen and this whole chain. So it means this cannot have a geometrical isomer. Why? Because a carbon is having like one carbon, which is having a double bond, is having identical groups attached. For geometrical isomer, it should be like two atoms or group of atoms which are having different mass should be attached to the that same carbon. Hydrogen can be attached to another one. This, when we check this carbon, hydrogen is there in this chain. They are different, but this one does not have a difference, so this does not exhibit a geometrical isomer. What about the last one? When we check, this two carbon are there, this will have hydrogen or hydrogen, and this is having one side this chain and another side this. So these are two different groups, but if you check the first right hand side carbon with a double bond, that has both hydrogen attached, so it cannot exhibit a geometrical isomer. When we check this central carbon-carbon double bond, so this is one group, this is another group, this will have hydrogen and this another group. So here you can see that these two are different groups and these two are different groups. So this double bond will exhibit a geometrical isomer. That's why we circle this one. Draw a skeletal formula of other geometrical isomer. So if you want to draw, look, if you see which geometrical isomer is this, when we check the heavy groups, so these two, this is heavy. And when we check the heavy group, so this is heavy. So it means heavy groups are like one is up, another one is down. So it is trans, like opposite. If it was same, then it will be cis. Cis or Z, trans or E. So if we want to draw another, so we just have to switch these positions. Like we draw in the same manner. This structure we draw up. 1, 2, 3, 4. So this will, because now what will happen, this will become opposite. Before it was like heavy groups, one is top, one is bottom, but now both of them are at the top. Is it clear? The geometrical skeletal formula of the geometrical isomer. Or you can switch the first one as well. Like you can also draw, if you want to draw, you switch these two. That will, if you want to, you can switch these two as well. Like this part, I will just switch. So one carbon is there and this down is two carbon atom with the double bond. And then I will draw the same structure. So this is also, as you can see, the heavy groups with reference to the carbon-carbon double bonds are on the same side. So that will also become cis. Then in an experiment, 0.05 moles of alpha ocumen reacted with 3.6 dm cube of a hydrogen in the presence of the catalyst. Nickel is used as a catalyst here. Deduce the structure of deduce the structure of the product of this reaction. You must show your working. First, what we'll do, we'll find a mole ratio between them. Like, because like how many, as we know, we need because there are double bonds or three double bonds are there. So maximum 3 molecules of hydrogen can react. But first we'll take a ratio between the alpha ocumen and the hydrogen, and we'll work out what is the mole ratio. And then if two hydrogen are there, then there will be two double bonds break down. If three hydrogens are there, then there will be three hydrogen breakdown will be there. Like all the three bonds will break down. If one is there, then one. So we already have the moles of this. We'll work out the moles of hydrogen. So the moles of hydrogen, moles equal volume in dm cube divided by 24. So volume in dm cube is 3.6 and 24. So 3.6 divided by 24, that will give us 0.15 moles of hydrogen. Now, what is the ratio between the alpha occupant and the hydrogen? Like if we have 0.05 moles, according to equation 0.04 moles reacting with 3.6 dm cube or 0.15 mole. So to take a mole ratio, we divide it by the smallest value. We divide by 0.05. This will be 1 and this will be 3. So it means if we have one molecule of this, we need 3 hydrogen molecules to react. And if 3 hydrogen molecules will react, so all the double bonds will break. So what will be the structure here? This was a structure of a reactant, and it is reacting with 3 hydrogen. So 2 hydrogen will break, like double bond will break here, double bond will break, and double bond will break. So all these double bonds will break and it turn into a single bond. So this double bond break down. This double bond will break down. And this double bond will also break down. So as a result, when 3 hydrogen react, all the double bonds will break down and it turn into all the single, means saturated hydrocarbon. So we have to draw the structure in the last part. So this was a pop quiz 19, which was related to organic chemistry.